Video for the worksheet with permutations on one side, combinations on the other side. Hopefully this worksheet will help you understand the difference between permutations and combinations and how to connect them to word problems, and then also how to evaluate them numerically. All right. So complete the following table by providing the missing information. We'll start on the permutation side. The manager of a baseball team has named the 9 starters for the game. He needs to determine the batting order. How many batting orders are possible? Fill in the blanks with how many ways you can fill each space. So check real quick, there are 9 spaces here. That could be like your batting order. Probably there's normally 10 spots. We're assuming maybe saving the last spot for the pitcher. So how many ways can you fill in this first spot? Well, he's got 9 players, so he can fill it in with 9 people. But when we move to the second spot, that first one's already been filled, so there's only 8 people remaining. So now there's 8 spots remaining. And then 7 people remaining for the 7th spot, 6, then 5, then 4, then 3. And when it gets down to the last 2, there will only be 2 people left, so he's got 2 choices for this one, and then the only person remaining will get that 9th spot. All right, this should look familiar. The fundamental counting principle says if event 1 can happen m ways and event 2 can happen n ways, then their combined number of ways is m times n. Well, we just expand that out and we multiply all of these. And that's what's happening in this formula here. 9 factorial is 9 times 8 times 7, and so on. Then we get rid of any numbers at the end that don't actually get filled. Like if the 9 people were only filling into 5 spots, we would stop after this 5. That's what the bottom of this formula takes care of. But here we go all the way to the end, so we divide by 0 factorial, which is 1, and 9 factorial. Let's just double check that. 9 math factorial is 362,880. All right. There are 33 cars in a race. The first, second, and third place finishers win a prize. How many different arrangements of the first 3 positions are possible? So you got 33 cars that could come in first, but that car has already passed the line, so there's 32 cars remaining on the track, and then there's 31. We're going to multiply these. All right, let's put this into the formula the way that it shows us. So first we got to write it with the p's. So it's 33 pick 3. That's how I say that. This is going to be 33 factorial divided by n minus r, so 33 minus 3, so 30 factorial, which equals, let's figure this out, 33 times 32 times 31. There are 32,736 ways first, second, and third can occur. Okay, next column, we just see 10,987, and we know that that's 5,040. So what's happening here, this is a 10 pick how many? 1, 2, 3, 4 situation where we did 10 factorial over 6 factorial. But what could be the word problem for this? I'll let you think for a second what could be happening here. Let's see, we've got baseball, cars, license plates. On the other side, baseball, committee, pizza. We got to pick something that's different than all of that. Let's say we have 10 books. We are going to read 4 in order. So order has to matter for permutations. So you got 10 to pick from. When you read that first one, now you got 9 to pick from. You read that one, now you got 8 to pick from. And order matters. So effectively, I'm not going to write out the question, I'm going to run out of space, but how many different ways can this occur? All right. The license plates in a certain country contain a permutation of exactly 5 letters. If no letter can be repeated, how many permutations are possible? So in that first spot, put 26. Second spot, you put 25, then 24, then 23, then 22. This is 26 pick 5, which is equal to 26 factorial divided by 21 factorial. And I'm going to plug this into my calculator as 26 times 25 times 24 times 23 times 22. And we get 7 million. 7,893,600 different possible license plates. All right, can we write another scenario where we're only given this? 7, pick 4. Let's make sure this is done correctly. So we need to have 7, then 6, then 5, then 4. So we're picking 4. Let's calculate what that is. $840. I'll leave this blank. As long as you've got 7 objects and order does matter and you're picking 4 of them, you can come up with whatever you want there. All right, combinations. So the manager of our baseball team has selected the 9 starters for the game. She has 11 players to choose from. How many combinations of the 9 players can she choose? So in this scenario, order doesn't matter. You're either in or you're out. So this is a 11 choose 9 situation. There's the formula for how you crunch it, and there's 55 combinations. Here it says don't list like the number of people's per spot because there's not spots. It's just an example of one possible outcome. So we just need to come up with 9 names. Here I'm going to pause the video and come up with 9 names. All right, so there's my 9 starters: Abe, Joe, Steve, Bill, Bob, Henry, Ruby, Dylan, and Zach. All right, and then 2 people had to have gotten left out. So we'll say their names are Matt and Nick. All right. A committee of 5 students is to be selected from a class of 20. Here doesn't matter, order doesn't matter. So how many different committees are possible? Example of one possible combination would be students 1, 5, 7, 19, and 20. They're in order here, but it doesn't really matter what order. So the math that's happening here is we have a 20 choose 5 problem. And that's going to be equal to 20 factorial divided by 15 factorial times 5 factorial. A good check on this is that these 2 numbers always add up to this. And I always kind of think of it as these are the 5 that are in the committee, these are the 5 that are left out. And we can double check that that's right. 20 factorial, press enter, divided by, in parentheses, 15 factorial times 5 factorial equals 15,504. Yep. All right, we got to come up with our own example again. We have a 9 choose 3 problem. So we haven't done ice cream yet. Ice cream's like the best one. So you have 9 flavors of ice cream. How many bowls of 3 different flavors are possible? So I always like to come back to this ice cream analogy where permutations are cones and combinations are bowls, because with cones, order does matter because they're stacked one on top of another. In combinations and bowls, order doesn't matter because all the scoops are next to each other and you can just turn your bowl to see a different combination and it really doesn't change. So we need an example. So I'm going to make it a very fruity ice cream bowl with peach flavor, strawberry flavor, and vanilla, which is a perfectly fine flavor. And let's evaluate what this is. So 9 factorial. You can do 9 math, that factorial button, divided by, in parentheses, 3 factorial times 6 factorial, and I get 84. 84 different ways to pick 3 different flavors of ice cream from 9 possibilities. All right, Ciro's Pizza includes any 5 toppings from the list of 16 toppings. How many different combos of pizza are possible? So I'll let you come up with this one as long as you have 5 toppings. So 1, 2, 3, 4, 5. All right, the math for this would be there's 16 possibilities. So 16 choose 5. This can equal 16 factorial over, so we need to split it into the 11 you don't choose and the 5 you do choose. 16 factorial divided by 11 factorial times 5 factorial equals 4,368. Okay, I'm going to leave this last one to you. Does it look right? Yep. The math here is solid, but you got to come up with your own situation for a 7 choose 4 situation. All right, and don't forget to fill in these pizza toppings here. And have a good rest of your day.